everyone. So in this video, we're going to be learning about a different approach to trigonometry. So we'll see that for certain angles, you can use right triangles without the context of the unit circle in order to evaluate the trigonometric functions. So this is the approach to trigonometry that a lot of people are taught first. So there's a good chance that a lot of you have actually seen this kind of approach to trigonometry before. But yeah, so basically, how have we been approaching trigonometry so far? Well, we've been defining the trigonometric functions using the unit circle, right? We said that for any angle, if you can go and sketch that angle on the unit circle and look at what the coordinates of the terminal point are, that's all you need in order to evaluate sine, cosine, tangent, etc., all of the trig functions. So the advantage of this approach to trigonometry, and really the reason that I like to do this approach first, is because this approach works for any angle, right? You can go to an angle of, negative 100 pi and see where that is on the unit circle and find the terminal point. You can do an angle of, 25 pi over 4. You can do these really big, really small, negative, positive, any kind of an angle, the unit circle definition is going to work. So the approach that we're going to be talking about today is right triangle trigonometry, and we'll see that right triangle trigonometry really only works for angles that are between 0 and 90. So what is special about angles between 0 and 90 degrees? I'll say 0 degrees and 90 degrees. Well, those are angles that can fit within a right triangle. Right, so a right triangle always has one 90-degree angle, and the total amount of degrees in a triangle cannot exceed 180. And so the other two angles in that right triangle, right, besides that right angle, those two angles cannot be bigger than 90. They have to be actually strictly less than 90. And similarly, it just doesn't even make sense to have a negative angle within a right triangle. So these are angles that can fit within a right triangle. Whereas, when we're talking about any angle, so large angles, negative angles, etc., those are examples of angles that cannot fit within a right triangle. And so again, that's kind of the advantage of using the unit circle is it expands what kind of angles you can evaluate trig functions for. But we'll see that the right triangle definition is going to be really handy in some cases, especially in doing some real world applications, which we'll get into in our next video. Okay, so how do we define these trig functions? Well, if you have an angle, we're going to call our angle theta, and that angle is within a right triangle. So notice here I use the word acute. So acute just means less than 90 degrees or between 0 and 90 degrees. So this is saying that theta is between 0 and 90 degrees. And that's basically what we said above, right? In order to have an angle that fits within a right triangle, it just has to be between 0 and 90 degrees. And by the way, you might notice that I've been using degrees so far in this video. In the context of right triangle trigonometry, we do use degrees a little bit more than radians. There's no real particular reason for that, but you will see that in this video, we're going to be using degrees a lot. But don't forget about radians. We'll definitely be getting back to some other stuff with radians a little later after we're done with right triangle trig. Okay, so how do we define all these different trig functions? Well, basically, if you have a right triangle and your triangle contains this angle theta, we can label the different sides of this triangle kind of related or relative to theta. So I'm going to label the side that is across from the angle. I'm going to label that as being called the opposite side, right? Because it's directly across from the angle. And then the side that is not across but next to the angle, I'm going to call that the adjacent side. And basically adjacent is pretty much just a fancy way of saying next to. So that's all that means. And then the hypotenuse, I'm going to label that as the hypotenuse because that's what it's called. And so basically the definition of the different trig functions is going to involve taking different ratios of these sides. So for example, if you wanted to take sine of theta, that is going to be equal to the opposite side, so I'm going to abbreviate that as OPP for opposite, divided by the hypotenuse. If you want to take cosine of theta, that's going to be equal to the adjacent side, so I'll label that, or I'll abbreviate that as ADJ, over the hypotenuse. And then what about tangent? Well, we learned when we were using the unit circle definition, and we'll see later on in this video that even though this definition feels really different, it's actually equivalent to the unit circle definition as long as you're looking at angles between 0 and 90. So we know, according to the unit circle definition, that tangent is supposed to be sine over cosine. So what would happen if we took sine, so opposite over hypotenuse, and divided that by cosine, which is adjacent over hypotenuse? Well, the hypotenuses in the denominator would cancel out, and we'd be left with opposite over adjacent. And so the way that we define tangent is that it's the opposite side over the adjacent side. But again, that is still the same as really just saying sine over cosine. It's just kind of a simplified way of writing it. And then the reciprocal trig functions work really the same way you would expect. So cosecant, that is the reciprocal of sine. And so if we're taking the reciprocal of sine, that means that it's going to be the hypotenuse over the opposite side. So we're just basically flipping each of these fractions over. And so similarly, secant is the reciprocal of cosine. And so when we flip that over, we get hypotenuse over adjacent. And then finally, cotangent is going to be flipping over tangent, and so that is going to be adjacent over opposite. Over opposite. Okay, so I want to get into an example pretty soon, but there's one quick thing I just want to mention. So notice that all of these sides are being labeled relative to theta. So for example, if I were to make theta be a different angle in this same triangle, so let's say that I instead wanted theta to be this angle. So if I just, forget about that one. If I decided to label this angle as theta, well then this side would become the opposite and this side would become the adjacent, right? Because now theta is across from this side and it's next to the other side. So basically, just make sure that when you're working with right triangle trig that you're paying attention to which angle you're actually focusing on and thinking about the adjacent and opposite sides as being kind of in relation to that specific angle. So they're not like specific sides of the triangle. They can change depending on which angle you're actually looking at. Okay, let me just erase this. Okay, so let's jump into an example. So let's say that we have a triangle here. So we're given a triangle with an angle theta, and we want to evaluate all 6 of the trig functions for this angle. And so it's basically just going through the definitions we said on the last page, right? So we know that sine of theta is supposed to be the opposite side over the hypotenuse. So in this case, that's going to be 3, right? That's the side that is opposite of theta over the hypotenuse, which is 5. And then cosine, well, that's going to be the adjacent side, so that's 4, over the hypotenuse, which is 5. And then tangent is going to be the opposite side over the adjacent side. So the opposite side is 3, and the adjacent side is 4. And then to find the reciprocal trig functions, we just take the reciprocal of each of these. So cosecant is going to be 5 over 3. Secant is going to be 5 over 4. And then cotangent is going to be 4 over 3. So one thing I just want to point out, that's kind of an interesting thing to note. So remember that based on our unit circle definition and based on the graphs of sine and cosine, we said that sine and cosine must be less than 1, right? The range of sine and cosine is from -1 to 1. And we'll see that sine and cosine are not going to be negative when we're doing right triangle trig, but it is true that they are never going to be greater than 1. And so how can we see that? Well, remember the hypotenuse is always the longest side in your triangle. So if you're doing a ratio where you're doing, either the opposite or the adjacent side, and then you're dividing those by the hypotenuse, because the hypotenuse is the biggest side in your triangle, those fractions are always going to be less than 1. Because you're comparing a shorter side to a longer side. So any fraction where the numerator is smaller than the denominator will be less than 1. So I just wanted to kind of point that out. Okay, so one thing that is important to realize about right triangle trigonometry, and this will help us in a moment to also connect this back to the unit circle, is that the specific triangle that you draw with that angle in it actually doesn't matter. And so why is that? Well, it basically has to do with similar triangles. So remember that we talked about similar triangles at the beginning of the quarter in our kind of geometry review section. And I told you that similar triangles basically means that they have the same 3 angles. And additionally, because they have the same 3 angles, they really have the same shape. And one way of describing the fact that they have the same shape is saying they have proportional sides. And so that basically means if you compare side lengths, if you take a ratio of side lengths within a triangle and then take a ratio of the same side lengths within the similar triangle, you're going to get the same ratio. And trigonometry, right triangle trigonometry, is all about ratios, right? We're doing opposite over hypotenuse. We're always comparing different, we're building these ratios from the sides of the triangle. So if you have a right triangle, and you know it contains a specific angle. So for example, maybe this one, we have this angle theta. We don't know what theta is, but we know that this angle contains, or this triangle contains a specific angle theta. If we draw any other right triangle that also contains this angle theta, it's going to be a similar triangle to this one. So how do we know that, right? Similar triangles are supposed to have all 3 of the same angle. So I'm telling you that actually just having one of the same angle is enough. And so why is that? Well, it's because we also know that this angle is 90, right? We're talking about right triangles here, right? So I said any 2 right triangles that contain the same acute angle theta. So if you know that your right triangle contains theta, you know that it's a right triangle, so it also has a 90-degree angle, well then the third angle is always going to be the same, right? Because it's just going to be 180 minus whatever the sum of these 2 is. And so any other right triangle that you can draw that also contains this angle theta is going to be similar to this triangle. And so why is that important? Well, because like we just said, right triangle trig is about ratios. So if you have 2 triangles that are similar and you use both of them to calculate sine, cosine, tangent, etc., well, because you're taking ratios, if those triangles are similar, the ratios are going to be the same. So I want to really convince you of that. Let's say that we have a triangle, and let's say this triangle has the exact same angle theta. So this angle theta that we had above here, again, we don't know exactly the value of this angle, but let's say this is the same exact angle. And let's say that this triangle is exactly twice as big as this triangle. So if it's twice as big, that means all of the sides are going to be twice as long, right? So this side is going to be 6 instead of being 3. This side is going to be 4 instead of being, it's going to be 8 instead of being 4. And then the hypotenuse is going to be 10 instead of being 5. So we don't have to do all 6, but let's just do sine, cosine, and tangent just to really see that we get the same answer as we did above. So if we take sine of theta, so sine is supposed to be opposite over hypotenuse, so that would be 6 over 10. But 6 over 10, well, that reduces, right? So that would reduce to being 3 over 5. And if you go back to the original triangle we used, so sine of theta, we just saw that it was 3 over 5. Well, up here we also got sine of theta is equal to 3 over 5. And really, it's because this ratio is being preserved, right? Because these two right triangles have the same angles, they have the same shape. And so that means that whatever is going on when you compare these two sides, you're going to have the same comparison happening in any triangle with that same kind of shape. And so similarly, we can just do cosine of theta and tangent of theta really quickly to see that those also come out the same. So cosine would be 8 over 10. And so that reduces to 4 over 5. And if you go back up to the original triangle we did, we got the exact same thing. We got 4 over 5. And then finally, if we do tangent of theta, well, that is going to be opposite over adjacent. So that is 6 over 8. And 6 over 8 is going to reduce to 3 over 4. And again, that is the same as what we got in the above triangle. So my point here is that as long as your angle is the same, it doesn't matter what specific triangle you're drawing or using as your reference, because those triangles are going to be similar, you're going to get the same answer. So typically for this kind of problem, you are given just one specific triangle, but I just want you to know that you always could have a different triangle with that same angle, and you would still get the same result. Okay, so this kind of connects to the next thing I want to talk about, which is you might be wondering, like, what about the unit circle, right? There should be some kind of a connection between these two definitions, because otherwise they would be kind of competing with each other, right? For example, if I asked you to evaluate, sine of 30 degrees or something like that, you would be like, well, should I use the unit circle or right triangle? And, you should get the same answer both ways. And so I want to really convince you that when we're talking about angles that are between 0 and 90, you do get the same result using the unit circle or using a triangle. And I want to kind of show you why that is. So let's say that theta is still the same angle that we were working with on the previous page. So I just kind of sketched theta on the unit circle. It looks something like this. So how does the unit circle work? Like, how do you go about, finding sine and cosine and tangent using the unit circle? Well, you want to find the coordinates of the terminal point. And the way we've typically done that is by drawing a right triangle, right? We take our angle and we draw a right triangle. And the hypotenuse is 1, right? So now let's say that this triangle here is that triangle. So just imagine I'm kind of taking that triangle, bringing it out from the unit circle. So the hypotenuse in this case would be 1, right? And so again, this is the same angle theta from the previous page. So let's maybe draw another triangle with that same angle theta whose sides we already know, right? So the first example we did, the hypotenuse was 5, the opposite side was 3, and the adjacent side was 4. And so the small triangle, the one on the left, the one that kind of came from the unit circle with a hypotenuse of 1, well, that should be similar to the bigger one, right? These two triangles should be similar to each other because they both have that same angle theta. And so what would the other two sides end up being on this triangle? Well, notice that the triangle on the right is 5 times bigger than the triangle on the left. Or another way of saying that is that the triangle on the left is going to be 1/5 of the size of the triangle on the right. And so that means that the opposite side is going to be 3 over 5 instead of 3, right? It's going to be 1/5 of the size, so it's going to be 3 divided by 5. And then the adjacent side is going to be 4 over 5. And so the coordinates of our terminal point would be 4 over 5 as the x coordinate and 3 over 5 as the y coordinate. And so if we were to use this triangle and this point to evaluate sine and cosine, we would find that cosine would be equal to 4/5 and sine would be equal to 3/5, right? Just kind of using our unit circle definition. So this would be cosine of theta and this would be sine of theta. And that's exactly what we got on the last page, right? When we did the same angle, we said that sine of theta was 3/5, cosine of theta was 4/5. That's what we just also found using the unit circle. And so why does this work? Well, basically because of similar triangles, because the tiny little triangle that you're drawing on the unit circle that has a hypotenuse of 1, that's going to be similar to some other triangle that you could also use to evaluate sine, cosine, tangent, etc. And then additionally, if you look at this tiny triangle, if you were to evaluate, let's say that maybe you're forgetting about the unit circle for a second. So forget about the unit circle. Let's just focus on this triangle. If you were to evaluate sine and cosine and tangent using this triangle, well, the hypotenuse is just 1. So if you evaluated sine using right triangle trig, you would have 3/5 over 1. Cosine would be 4/5 over 1. And then tangent would be 3/5 over 4/5, which simplifies to 3 over 4. So basically, what's going on in the unit circle is really equivalent to what would happen if you just used right triangle trig. It's just that this really only works when you're in quadrant 1. Right? Quadrant 1 is the part of the unit circle where your right triangles are going to directly contain the angle you're working with. As soon as you go into another quadrant, like let's say you're over here and this is your angle theta. Well, now the right triangle you draw no longer directly contains theta, right? It has some other little angle here. It doesn't actually contain this huge angle theta. And so in order for these two definitions to really both make sense, you have to be in quadrant 1. So I just want to write that down. So as long as your angle is in quadrant 1, evaluating trig functions using the unit circle will give you the same results as right triangle trigonometry. And really, the only reason that it doesn't work when we're not in quadrant 1 is just because we can't draw a right triangle with those angles, right? You can't draw a right triangle with like a 300-degree angle. That just doesn't make sense. And so that's why we have to use the unit circle for those types of angles. Okay, so I want to do a couple more examples that are a little bit different. So first example I want to do is now we're not given all of the sides of the triangle, right? So on the examples we've done so far, we were kind of already handed a triangle that had sides labeled. So in this case, we're actually told that cosine of theta is equal to 3/7, and we want to kind of use that information to figure out what the other trig functions are. So when you're given this information that cosine of theta is equal to 3/7, we want to start by drawing a right triangle. And I guess one thing I should have added here is that in this case, we're assuming that theta is an acute angle. So maybe, let me just write that there, here. Theta is an acute angle, so meaning it's between 0 and 90. And so the reason that I need to add that fact is because otherwise we can't just draw a triangle. Otherwise, you would need to actually use the unit circle and kind of consider whether things could be positive or negative. In this case, we know theta is an acute angle, and so we can just go ahead and draw a triangle. Okay, so I drew a triangle already. Let's figure out which angle would make sense to call theta here. So it's saying that cosine of theta is 3/7. So remember that cosine is supposed to be equal to adjacent over hypotenuse. And so that means that, we have 3 over 7. So the 3 part, well, that has to represent the adjacent side. And then the 7 part, that has to represent the hypotenuse. And so we can go ahead and maybe label this angle theta, right? Because it looks like this is the shorter side. And so that would be the adjacent side, and that would be 3. And then the hypotenuse would be 7. So how can we find this remaining side? In order to evaluate the other trig functions, we need to know what this side is, right? And so how can we find that side? Well, we can just use the Pythagorean theorem, right? If you know 2 sides of a right triangle, you don't need to know the angles. You can always just find the third side just using the Pythagorean theorem. So, we could call this side like B or something, and then just use the Pythagorean theorem. So the Pythagorean theorem would say, you would say 3 squared plus b squared is equal to 7 squared. And so we'd get 9 plus b squared is equal to 49. And so that means that b squared is equal to 40, right, if we subtract 9 from both sides. And so that means that b is going to be equal to the square root of 40. And that can be broken down into the square root of 4 times the square root of 10. And so that would be 2 times the square root of 10. So by the way, remember when we were doing all the stuff with like the Pythagorean identity on the unit circle? In those cases, we always had to say plus or minus. In this case, we don't have to say plus or minus, and that's because we're assuming that we're within a right triangle. Because we know that theta is an acute angle, we don't need to worry about all these different ways that theta could be oriented that could cause us to get negative values for sine. In this case, everything is just positive. We're talking about a triangle. Triangle side lengths have to be positive numbers, so we can just say, okay, it's equal to positive 2 root 10. So now that we have that, now we can find the other trig functions, right? So now we can say, okay, we know that sine of theta is supposed to be equal to opposite over hypotenuse, and so that's going to be 2 root 10 over 7. We know that tangent of theta is supposed to be equal to opposite over adjacent. And so that's going to be 2 root 10. That's our opposite side we found, divided by 3. That was the adjacent side that we were given. And then we can find our reciprocal trig functions as well. So secant is the reciprocal of cosine. And so secant is going to be equal to 7 over 3. And then the reciprocals of sine and tangent, we can find those as well. So cosecant of theta would be equal to 7 over 2 root 10, which we probably want to go ahead and rationalize that, right? So if we rationalize that, we end up getting, if we multiply by square root of 10 over square root of 10, we'll get 7 root 10 over 20. And then for cotangent, that's the reciprocal of tangent, and so that's going to be 3 over 2 root 10. And so similarly, if we rationalize the denominator, so if we multiply by root 10 over root 10, we're going to get 3 root 10 over 20. So basically, if you're given information about, and again, this is kind of like when we use the Pythagorean identity, right? If you're just given information about, what one of the trig functions is, sine or cosine, you can find the other trig functions. And so in this case, it's just that we know that theta is acute, and so we can use a right triangle instead of using the unit circle. So I want to do one more example. And this example is going to be a little bit different because so far, in all the examples we've done, we have not actually known what angle we're working with, right? We've just been kind of given a generic angle theta, right? Here we're just like, suppose that cosine of theta is equal to 3/7. We never actually figured out what theta was. We kind of relied upon the fact that we were given those side lengths. And then similarly on like the second or the first example we did in this video, we did not know what theta was. We relied upon the fact that the sides of the triangle were all kind of filled out for us. But for certain angles, such as 60 degrees or 30 degrees or 45 degrees, we can actually fill out the sides of a right triangle in order to use right triangle trig without having to have them be given to us, right? And so let's say that we're, if we're evaluating sine and cosine of 60, let's say that this is our 60 degree angle. And so that would mean that the other angle in this triangle has to be a 30 degree angle, right? So that means that we're left with a 30, 60, 90 triangle. And so in order to evaluate the trig functions, we can actually draw any 30, 60, 90 triangle we want. We can really pick our sides. In order to really kind of show how it doesn't matter what sides we pick, I'm actually going to kind of label these generically. So what I mean by that is I'm just going to call this shorter side S, and I'm going to call the longer side So we know that the longer side of a 30, 60, 90 is s times the square root of 3. And then we know that the hypotenuse is 2 times s. So let's see what we get when we try to evaluate sine and cosine with this triangle. So sine of 60 would be opposite over hypotenuse. So that would be equal to s times the square root of 3 divided by 2 times s. And so how does this simplify? Well, we can cancel out the s, right? And we're left with just square root of 3 over 2. And we'll get into this in a second, but that agrees with what we would find on the unit circle, right? If you go to 60, that's a pi over 3 angle. We know that the y-coordinate on that point is square root of 3 over 2, and we'll get there in a second. But similarly, if we wanted to evaluate cosine of 60, well, we would do adjacent over hypotenuse, so that would be s over 2 times s. S's would cancel out, and we would be left with 1/2. And once again, that agrees with what we should already know from the unit circle, the value of cosine of 60 degrees is. And I really want to emphasize that we could have labeled these sides any way we want. You know, I chose to use just a generic s, but for example, we could have made this side, I don't know, 10. And then this side would be 10 root 3. And then this side would be 20, right? That would be like one specific example of a 30, 60, 90 triangle. And I would encourage you to go through evaluating sine and cosine, and you'll see that you get the exact same results using those kind of more specific sides than you would using these kind of generic sides that I put. And on that note, you know, what does it look like if we use the unit circle? So maybe let me just make a note here, you know, how does this compare to the unit circle? Well, if we were to go to a 60-degree angle, so again, that's pi over 3, now that we're a little bit more used to radians. So this would be our 60-degree angle. How would we approach this? Well, we would draw a little right triangle, right? And so our right triangle would look like this. And in this case, the hypotenuse would be 1, right? Because we're on the unit circle. And so we've learned using similar right triangles that the shorter side is 1/2 and the longer side is square root of 3 over 2. And so if you went through and actually evaluated, or if you then use this to find the coordinates of the terminal point, it would be 1/2 for the horizontal coordinate and square root of 3 over 2 for the vertical coordinate. And that exactly agrees with what we found above, right? Cosine of theta would be 1/2, sine of theta would be square root of 3 over 2. And additionally, that agrees with what you would get if you used right triangle trig with this triangle, right? If you did opposite over hypotenuse, the hypotenuse is 1. And if you do adjacent over hypotenuse, well, the hypotenuse is just 1. So that really hopefully convinces you that what's going on with the unit circle is really exactly the same as what we're doing here, as long as you are working with an angle between 0 and 90. So as I mentioned in our next video, we're going to be doing a few kind of applications of right triangle trig so that you can see, you know, why is this a useful thing to do rather than always using the unit circle. So I'll see you all in the next video.